electrics, photocatalysis, and all these things. And today I'm going to talk about the ultramagnets. Actually, my topic was non-relativistic spin splitting in ultramagnets. And generally, we are working on FeSB2, that is iron antimony type of materials. As Professor Dr. Gaurav has already introduced me, like I'm Dr. Dibya Prakash from Department of Physics, Mizoram University. Currently, I'm working here. So introductions, let me read the introductions, why we are going to this kind of materials, why we are choosing this kind of materials, because over the last 2 decades, spintronics has gained a lot of interest because it has so many promises. As those who are working in the field of like magnetic materials or Hessler or metal oxides, magnetic type of materials, then probably they knows about the spintronics. So because spintronics has a lot of promises for next generation's technology, like it will consume less power, and it offers fastest transfer of informations, and the capacity of storing data will be very, very high. So that is what we expected from the spintronic devices. So traditionally, spintronic devices has a component of ferromagnet types of materials. Ferromagnets, all of you know about the ferromagnets, and ferromagnets are considered to be the most like important components of the spintronic devices, because it has the spin polarization in its spintronic applications. Spin polarization is crucial because it will facilitate the spin injection. In spin injections, as you know, that it will treat as the data transformation. So spin polarization is very crucial in spintronic devices at the Fermi level. It has to be at the Fermi level because the transformation, the transport properties all deal with the Fermi energy. Okay, so the drawback of ferromagnetic material is that it constantly having a damping problems. So because of the damping problems, the information that has to be transferred, it is slow, and it will consume a lot of energy, because if the damping is there, it acts like a rinse, okay, for transformations of the data. So ferromagnets has that kind of drawbacks. It's a problem. Then let's come to the antiferromagnets. Antiferromagnets, on the other hand, has a very fast switching mechanism. It is in the ultra fast. It is the ultra fast in the range. Okay, so spin dynamics is very, very fast in anti ferromagnets. So people consider the antiferromagnets are the better components for the spin related technology. Okay, but the problem here in the antiferromagnet is there is no like generacy of the bands. So there is no spin polarization at the Fermi level. So spin polarization is crucial. Okay, at the same time, spin transfer is also crucial. So these two is, if you take ferromagnets, you have a spin polarization, spin injection will be there, but it will suffer a transfer of the spin because of the damping. On the other hand, the spin transport or the spin dynamics is very fast in antiferromagnets, but it doesn't have any spin polarization. So these two are like contradictory, like which is the best things. Okay, so now the new type of materials has been discovered in 2022. It's a very recent discovery. This material has been discovered by Libor Sumakel and the group from the Czech Academy of Science, and he has a double affiliations, and one is Johannes Gutenberg University in Germany. So this guy has given another concept on the magnetism. So other than like conventional two types of magnetisms like ferromagnets and the antiferromagnets, he has proposed another type of magnetic materials that is called ultramagnets. So ultramagnets has a new class of magnetic ordering. It's combined the characteristic of both ferromagnets and antiferromagnets. So this materials lies between the two ferromagnetic materials and the antiferromagnetic materials. Okay, so It exhibits spin splitting without the net magnetic moment. So antiferromagnets, the net magnetic moment is zero because the two atoms, two moments will be anti-parallel to each other, and the spin splitting is not present in the antiferromagnets. On the other hand, ferromagnet spin splitting is there, but the net magnetic moment is still finite in the case of the ferromagnets. Okay, so here in this case, in ultramagnets, it takes the flavor of both ferromagnets and the anti-ferromagnets. Okay, so from the ferromagnets, it takes the characteristic like spin splitting. Spin splitting is there in ultramagnets, but on the other hand, at the same time, it doesn't have any net magnetic moment, just like the anti-ferromagnets. So it takes the characteristic of both ferromagnets and antiferromagnets. In a simple way, I can explain like that. So spin splitting, it is coming from the ferromagnets, and net magnetic moment zero is coming from the antiferromagnet. So these combined properties of these materials um, looks very unusual, and it has the promises that whatever the ferromagnets or antiferromagnet cannot deliver for the purpose of spintonic devices. I think it can fulfill those all promises. Uh, so that is what expected. So origin of ultramagnetism lies in the symmetry allowed, and it allows the breaking of time reversal symmetry. So time reversal symmetry breaking is a very typical phenomena in the ferromagnetic materials, but it doesn't have in the antiferromagnet. Okay, so what kind of materials is ultramagnets? So I will spend a little more time. How much time do I have? Hello.
Sir, up to 11.
Up to 11. So okay. So yeah. So this is the prototype structures of ultramagnets. So the first materials they have proposed the ultramagnetic behavior was RuO2. So this is a tetragonal structures which has a space group of P42 M and M. Okay, so you see that the corner atoms and the central atoms are antiferromagnetically coupled. Okay, so now you see this one. So there are two atoms. The corner atom shares 1/8 that we have already studied in our basic physics. 1/8, 1/8, 1/8. So the corner atom's contribution will be 1. Okay, and the one which is sitting at the center is contributing its whole volume, that is 1. So there are two atoms, and the two atoms are anti-parallel to each other. Anti-parallel to each other. So because of that, their total magnetic moment is 0. So on the other hand, if you see the motif, this one motif or the basis, that means the atoms surrounded the magnetic atom. That is, the atom surrounded the magnetic atom are the oxygen atoms. You see how the oxygen atoms are distributed on the right hand side. So oxygen atoms are distributed in this fashion. Okay, so it is following a C2 C4 type of symmetry. Okay, C2 means 180-degree flip of the spin. Okay, when you flip the spin by 180-degree, but at the same time, like, the distribution of the oxygen atom is rotated by only 90-degree. You see on this one that black dots are rotated by 90-degree, but its spin direction is flipped by the 180-degree. So this is a two-fold symmetry and the four-fold symmetry. So this kind of materials are good for the I mean, this kind of materials are expected to have the ultramagnetic behavior. Okay, so a historical timeline. It was first discovered in 2022, and the first coined the word ultramagnet by Libor and his group on the prototype materials, that is ruthenium dioxide. This is the prototype materials, and there are, after that, there are so many works has been carried out in this field. So this is what I have found out from Google. So I directly paste out from the Google. The publication is like, it's galloping, and Now you see, like, how can we distinguish between the three types of the magnetic materials: ferromagnets, antiferromagnets, and the altermagnets. If you see the ferromagnets, you have seen this, the spin splitting is very clear. Spin splitting is very clear at the gamma point. Gamma point, you see the spin point, that is the red curve and the blue curve are separated. Okay, and you see the how the distribution of the charges, spin density of the spin density around the magnetic atom is looks symmetric. Here in antiferromagnets, uh, the spin density is completely spherical, and you will not find any splitting. So there is a band degeneracy around the gamma point. But if you come to the C, that is level C, you will see that how the this spin densities are arranged. So spin density are not exactly spherical, neither it is square shape. It is something like dumbbell shape or some kind of orbital type. Okay, so this kind of shape we call the spin density, the shape of the spin density, we call it the D wave symmetry. Okay, because it looks like the D orbital. Okay, then if you come down to the band, you will see the band exactly splitting is there, but it doesn't look like ferromagnet type. Okay, so it has a little different type of splitting. You will see the splittings around the two points, but exactly at the gamma point there is a degeneracy. Okay, so you see this one. The blue line is supposed spin up bands, and the red line is your spin down band. So there is a kind of symmetry it has followed. So this is called the automagnetic type of splitting. Okay, so this is then what are the distinctive features of automagnets? The first criteria is it has to be antiferromagnets. Okay, it has to have a zero uh, net magnetic moment. And another criteria is it has to have a splitting around the any high symmetry points. Okay, so you see here the gamma symmetry points. Then it should have the time reversal symmetry breaking. Okay, then time reversal symmetry breaking has to be there, and because of the time reversal symmetry breaking, it will have the finite Berry curvature. Okay, then there is a paper which describes about like how to select the automagnetic materials. So there are so many materials, antiferromagnetic materials are there, magnetic ferromagnetic materials are there, but among those materials we have to choose automagnets. So what is the criteria for choosing the automagnet? The first criteria is the number of magnetic atoms in a unit cell has to be pair. Okay, there has to be even, like 4, 2. Okay, it should not have an even I mean the odd number of magnetic atoms in a unit cell. In a unit cell, always it has to be a pair. Okay, the magnetic atoms with opposite spins in automagnets are not related by inversion symmetry. So there should not be related by the inversion symmetry. Uh, however, the magnetic atoms with the same spin configuration can be linked by inversion symmetry. Okay. Then next is uh, local environment. If you see the local environment, there should be a local motive pair anisotropy. Okay, so if you see this one, then whenever it is translating, it is going from one, suppose from center atom, when it is going towards the corner atom. Suppose if you go from center to the corner atoms, you will see the environment is not the same. So that is called the local motive pair. So this local motive is not the same. These two pairs are not the same. So its environment has been changed. Okay. So the opposite spin lattices are connected by rotation combined with the translation or inversion symmetry or mirror glide or skew symmetry. Okay. So whenever you see the spin, whenever you go from translate from one spin, one position to another position. Suppose you're going from the corner position to one corner position to another corner positions. It is uh, 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 it is protected by the rotation symmetry. Okay, spin clip. So these are the types of automagnets. So first criteria is there has to be a pair number of magnetic atoms in the unit cell. Second is the anisotropy in the environment, and third is the spin symmetry is protected by the rotation. Okay, so rotation symmetry. Then now there are three types of ultramagnets so far has been distinguished, and they are called D wave, G wave, and I wave. And the example of D wave symmetry is RuO2, FeSB2. So and its structure is looking like this. Then you have this kind of spin density wave. So spin density waves look like this. So you have there are two lobes, okay, two blue lobes and the two red lobes. Okay, so red is generally for spin down and blue is generally for spin up. So similarly here, in the G wave symmetry, you have multi-lobe angular profile with six-fold symmetry, and this kind of spin wave, this kind of spin wave you can find in a materials like CRSB and MNT. Okay, and others are also there. You have to find out. We have to find out. And I wave symmetry, it has 12 lobes, and in the K space, and the materials which exhibits this kind of spin density are like CRI3, and then you have FEB3. So these are the examples of the D wave, G wave, and I wave type of symmetry ultramagnets. And ultramagnets not only has been proved by theory, I mean explained by theory. This concept has already been explained by the theory, but experimentally also they have found this kind of behavior in a antiferromagnet materials. In an antiferromagnet materials, they have performed the ARPS probe, and they found the spin splitting, and they proved this is the magnet type of materials. And there are certain materials that I have taken this from review paper. Then CRSB2, CRSB2 is antiferromagnetically coupled. Their net magnetic moment is zero, but at the same time, the splitting has been observed from the ARPS probe. Okay, so there are so many materials that has been ultramagnets because they are antiferromagnets. At the same time, they are giving the spin splitting. This is all I have taken. The result. This is the results that I have taken from the experiment work. So now let's. There are a lot of these things, mathematical expression, but I will just go brief how it has been done. I mean, these things. Density functional theory is as usual. There we have to use the density functional theory for band calculations and all these things. But the core of this work is like how do we understand the splitting of the bands? Okay, so that is very crucial. So generally, the splitting of the bands, if you go to your basic physics, the band splitting comes from the Zeeman effect. Okay, when you apply the magnetic field, then there will be a splitting of the magnetic field. So experimental point of view, so that what we see, this is the picture. We will directly blame to the Zeeman effect for the splitting of the bands. And if you come to the theory side, then how this picture can be understood more clearly. That can be done with the help of spin orbit coupling. When you apply the spin orbit coupling in the theory, then it will generate the internal magnetic field. So this internal magnetic field is responsible for creating the band splitting. But in our case, in ultramagnets, there are no any magnetic field. So there is no spin orbit coupling. So this band splittings comes without the spin orbit coupling. Generally, in theory, band splitting comes under the influence of the spin orbit coupling. But here, we do not have any spin orbit coupling. Okay, so this we have to understand. Even if there is no spin orbit couplings, then how the band has been generated. So there has to be some internal magnetic field, but our calculations or DFT cannot capture or cannot trace those magnetic field. But what is that magnetic field that I will explain here in a brief. So the non-relativistic Hamiltonian looks like this. H is equal to P squared to M, that is the kinetic energy plus the crystal potential minus the potential due to the internal magnetic field. So mu r is the spin directions of spatially varying magnetic field, and h hat, this h hat is the non-uniform magnetic field there, and this mu r h r d uh, uh, D3R is 0. This is because this is the antiferromagnet materials. Okay, in antiferromagnet materials, you will see this term is 0. So how does our energy looks like? Interaction energy, magnetic, the interaction energy due to the magnetic field. How does it look like? So it looks like in the, like it is expanded in the power series of R. When we expand this in the power series of R, then our the internal energy due to the magnetic field looks like this. Okay, the first term, second term, and the third term and higher order terms are also there. So first term is this is antiferromagnets. So uh, this is antiferromagnets, and because of the antiferromagnets, the two the moments will cancel each other and it becomes 0. And what about this second term? Okay, so second term will also become 0. Okay, second term is also become 0 because of the symmetry. Okay, because of the crystal symmetry, second term is 0. The only term, only in our calculation, in our DFT calculations, the only term that we could capture is the first term. Okay, we can capture the first term. If it is a ferromagnetic, this the first term will exist. If it is antiferromagnet, then this first term will not exist. Okay, so only up to here we can capture in our DFT calculations. The rest of the two terms cannot be captured. Okay, so but there are some other cut like ELK and all. We can capture the higher order magnetizations also. We can capture, but in ultramagnets, these two are 0. Okay, first term and the second term is 0. The only responsible term, because we are having spin splitting, right? So in spin splitting, there has to be some uh, magnetic field that will split the band, just like in the case of G-man effect and the spin orbit coupling. But our that the magnetic moment, dipole moment, the total magnetic moment is 0. Instead of this magnetic moment is 0, we are having a spin splitting in the case of the automagnets. So that we are trying to find out the hidden concept, what is there. So the first term is 0, the second term is 0 because of the crystal symmetry. Because in this kind of materials, this is a centrosymmetric type of materials, and it is a centrosymmetric type of materials, and it has uh, uh, because centrosymmetric materials, and it has the inversion symmetry. So because of the inversion symmetry, the second term will not exist. It is 0. Okay, so then the only possibility is the higher order term, and that higher order term is the third term. This third term is the second order gradient of your magnetic field. Okay, so internal magnetic field. So this term is related with the octupole moment. So octupole moment will give you the intrinsic magnetic field. So this third order is responsible for giving you the spin splitting in the spin splitting in the ultramagnet types. So because of that, there is a spin splitting, and there is a internal magnetic field which is comes out of the your third order magnetization, third order sorry, second order derivative of your magnetic field, that basically give you the octopolar moment. Okay, so and as a result of this, it will give you the spin splitting, and it will break the time reversal symmetry. So once the time reversal symmetry is broken, then we have this Berry curvature. Then we have a finite value of Berry curvature, and if you integrate the Berry curvature in the uh, uh, first Brillouin zone, we will get the anomalous Hall conductivity. That I will come to the next slide. So how can we measure the spin splitting? So spin splitting, generally you see in the picture, there is a spin splitting, that delta E is the spin splitting. Then you will see that this is this E plus minus K is equal to E0 K. E0 K is the bands that is without splitting, and delta K is the splitting factor. Actually, E delta K is the splitting factor. Okay, then how will we measure the strength of the this splitting? Okay, so we can calculate this non-relativistic spin splitting. Why it is called non-relativistic spin splitting is because this splitting is coming out without the influence of spin orbit coupling. There is no non-relativistic the, uh, the picture, okay, the influence in this case. So this spin splitting we can measure from this formula. Delta E is equal to delta Ek minus Ek Ek up minus Ek down. Up and arrow and down arrow represents the spin up and spin down. Okay, spin down electrons. Okay, and then the whole these things can be captured or mapped by this formula Fk sin kx a sin ky and a. This Fk is any k dependent function, and whereas a is the lattice constant. Okay. Now here as we have said that the internal magnetic field that comes from the octopolar moment will break the time reversal symmetry, and it will create the spin splitting, and as a result of that we will get the finite value of Berry curvature. And if we integrate the Berry curvatures in the presence of in the whole Brillouin multiplied by the Fermi Dirac functions, then we will get the AHC, that is the anomalous Hall conductivity. And this anomalous Hall conductivity and Berry curvature, this is the very typical features of the ferromagnet type of materials when you have the spin splitting. So I'll come to my result. I will explain my result. Basically, we did our calculations. Am I too fast? If I am speaking too fast, just stop me. And
okay, sir. Okay.
Yeah. Okay. So what we have done is like we have done the calculations of FESD2. First thing is like we have the choosing of the materials. We have found out this FESD2, which looks similar to RuO2, the prototype type of materials, and it has the similar this structure. And like our experimental group, they have synthesized this FESB2 materials, and they have performed the other characteristic calculations using the experimental tools and all these things, and they found that FESB2 was antiferromagnets. So antiferromagnets, but we could not confirm this is FESB2 is a pure antiferromagnet, or it has the like flavor of ultramagnetism as well. So that was a little bit suspicious, and beyond that they could not do any calculations because they do not have these ARPS facilities and all these things. They could only find out from their susceptibility calculations that FESB2 is confirmed antiferromagnets. So that is the foundation of ultramagnet that give us some hope. Then we performed the DFT calculations. So when we performed the DFT calculations, we found out the spin splitting, and this is the spin density that we have calculated for different pressure at 0 pressure and the 10 GPa pressure, and we found that the spin you see the spin environment around the Fe2 atom and spin environment around the Fe2 atoms in the figure A and figure B. You will see that it's shrinking. Okay, the shape is shrinking. So from there we can find out that if the shape is shrinking, then we can correlate these things and the spin splitting. The strength of the spin splitting is going down, and we have calculated the Fermi energy also. And Fermi energy also, it is very distinctive that the spin up and spin down is so clearly separated. So green color represent here in the figure A spin up, and the purple color represent the spin down. So spin up and spin down has been nicely separated separated in the Fermi surface. Okay, so and this one also, and 10 GPa also, we have found out the spin up and spin down is splitting. Okay, so this is what we found, and these results we have published recently in 2025 in Physical Review 3, and this is our findings. And we have found out that uh, the different bands contribution, we'll see that one. So splitting, we have just measured the spin splitting only around the Fermi level, because these are the bands which is important for like spin transport and all these things. So we are only concerned about the bands which is around the Fermi level. So the spin splitting, we have observed that the strength of the spin splitting is decreasing on increasing of the pressure, and uh, we have done only up to 10 GPa, and there might be a transition when these materials will completely becomes either ferromagnets or the antiferromagnets, that we have not checked so far. Only up to 10 GPa we have done. Okay, and AHC also we have calculated. We have used other tools called like 1 n 90. Using the 1 n 90, we have calculated the anomalous Hall conductivity of ESP2 under pressure, and 0 GPa, 1 GPa, and the 4 GPa and 10 GPa. We have already done the calculations, and we have found out the finite value of AHC, because there is a finite value of this Berry curvature, and as a result of that, we have also captured the anomalous Hall conductivity of these materials. So our results of AHC for FESB2 at ambient condition is matching with the result of ego imaging. So this paper, which is published in PNAS, we have compared our results with their results, and this is our results, and their results are matching. But we are not sure about the results at higher pressure, because there are no any uh, like already calculated data, or already like available data to compare our results. So maybe it's okay or not, because but at the ambient conditions it is matching. Okay, so and why we are using these materials is because these materials has a lot of promises in spintronic devices, as I have already explained in the introduction sections, and it can be used as the spin-based transistor in CMOS and quantum computing as well. And conclusions. So automagnetism is a new order type of magnetisms that has been really recently discovered, which is protected by the symmetry. Okay, and it has a spin splitting. And in our case, FeSB2 at the ambient conditions, we report 0.2 electron volt of spin splitting, and this kind of materials is a hybrid, having a hybrid characteristics of antiferromagnet and the ferromagnets, acts like a bridge between the ferro and the antiferromagnets. And to explain all these things, we need very strong theoretical and experimental backing. Only if we calculate goes up to antiferromagnets from the experiment, it is not sufficient, because we need more sophisticated tools, or sophisticated um, probe for explaining all these things. And generally for DFT calculation is also, it is very tedious. It takes a lot of time, because you have to go from like splitting, then you have to check the Berry curvature calculations, and they take a lot of time. So it's very time consuming. And so anyway, but this is a very unusual behavior type, and unusual behavior of behavior of FeSB2, which give the like flavor of automagnets. Okay, then this unique features enables new spintronics technologies. So I have already said the spintronic technologies require spin polarization and the spin dynamics, ultra fast spin dynamics. So maybe the automagnets fulfill those promises in this case. So we can see that ultramagnets has a brighter future in upcoming technology. So these are my references, and I would like to thank the organizers and to the participants. Thank you for your patience.
Thank you, sir. We are open for questions from the participants. Sir, I have one question. Dibya, sir.
Yes, sir.
Sir, how these ultramagnets are there? They are different from multiferroids.
No, multiferroics are different type of materials. Okay, here you this materials is in between the ferromagnets and the antiferromagnets.
Okay, so multiferroics are
Because
they are
you
like
see that no, but in multiferroics you will not have this zero magnetic moment and the splitting at the same time, right?
okay, sir. So I
And
think sir,
this pictures comes. This picture comes only if you are not using the spin orbit coupling. Generally, spin orbit couplings will enhance the splitting, right? But
sir,
here
I
in
think
this case, you have yes.
sir, I think this multiferroids, I think they have two properties, ferromagnetics and ferroelectrics, isn't it?
No, but here this is antiferromagnets, right?
Okay, sir.
This is antiferromagnets. Antiferromagnets, like the two atoms are uh, anti-parallel to each other, and their total magnetic moment is zero.
Okay, sir.
And at the same time you will have the spin splitting, right? This spin splitting you will not find in the antiferromagnets.
So how we can like synthesize these materials like sputtering or simple like ball
No,
milling
you
or
simple method also. We have our team has this one synthesized these materials using the sol gel method also.
soul gel method. Okay, sir.
Yes, although I am not expert in these experiment things, but they did the sol gel type of calculation.
Okay, sir. Participants, we are open for questions. Okay, you can write your questions also.
Yeah, you can ask questions. You can email me also.
Yeah, Dr. Dibya, nice presentation.
Hello, sir.
I like it. And the
Thank
tool
you, sir.
you are using is which tool you are using for this study? That's
Yeah,
software.
sorry, I forgot to mention this one. This we are using quantum
Quantum
espresso.
Okay, okay. Yeah, good.
Yes.
Participants, you can ask questions. Thank you, sir. Thank you, Dibya, sir, for this wonderful lecture.
Thank you.
And actually, I was aware about this ferromagnetics and ferroelectrics, multiferroics, but I did not know this ultramagnets, and
That
it's very.
multi-ferroid a different concept.
Uh,
It is as you know that multiferroids is like ferromagnets and like that polarization, right? Dielectric polarizations and all these things.
yes, yes, sir.
There.
Yes, sir.
But here that is not there. Here only we are talking about the antiferromagnet coupling, and even if having an antiferromagnetic type of coupling, but its outcome is like ferromagnets.
Okay, sir. Sir, one more request, sir. If someone is interested in working in this field or they want to collaborate, are you open for them or to accept their requests?
Yes, I'm open. Yeah, my group is always open for collaborations for any kind of work, not only related to this particular, the ultramagnets. So we are doing a lot of work. My research group is expanding. So I have like so many scholars and so many postdocs. They are working on different fields. We can collaborate in any field.
Thank
Our
you,
group
sir.
is
Thank you,
open
sir.
for all these kinds of work.
Sir, Pooja, I think Pooja wants to ask any question. Pooja, you can ask. Pooja, you can unmute yourself because I have given this permission.
We still have a lot of time. The time is up to 11.
Sir, Divya sir, few questions are there in the chat box. Can you see? SOC
So I
inclusion is, one question is, SOC inclusion is necessary or it can be skipped?
no. This is NRSS. Okay, non-relativistic. Non-relativistic means no spin orbit coupling. No, you are not. You cannot use SOC. Even without SOC, that's what I'm trying to explain. Even if you don't apply SOC, right, you will get the spin splitting. Generally, in antiferromagnets, when you apply the SOC, then you will get.
Hello. Uh, Hello. Good morning, sir. So thank you for delivering such a nice lecture, and it was really an interesting material. But inclusion of hello, am I audible?
Yes, you are
Yeah.
audible.
So
Yes, I can hear
because
you.
it contains RU, so I thought that SOC inclusion can change few things in DFT. I don't know about the experimental things, but in the DFT calculation, SOC inclusion, I mean, it seems that it it can be some important changes it can bring in
Yes,
the
correct.
cross or band structure.
Yes, exactly. So like why you are applying SOC is because I will explain you. I will correlate with the experiment and theory. Okay. So you see like when you apply the magnetic field to your materials, right? So you will observe this the splitting of the band that we have already studied in our BSc, right? So that is
Yes.
like a Zeeman effect, right?
Mm.
Zeeman effect in the experiment. Zeeman effect is the splitting of the band when you apply the magnetic field.
Yes.
In theory, what we do is we cannot apply the magnetic field directly, right? In theory. So in theory, to have the flavor of the magnetic field, what we do is we will apply the spin orbit coupling.
Mhm.
So
Yes.
when you apply the spin orbit coupling, then our expectation will be same as the G-man effect. Whatever the G-man effect will do, and spin orbit coupling will also do the same thing, right?
Mhm.
Okay,
Okay.
but here in this case, we are not applying any these things spin orbit coupling. So there is no any spin orbit coupling. So that means there is no magnetic field, right? So
Mhm.
despite of not having the magnetic field, applied magnetic field, we are getting the splitting. So that is the idea. We don't need to apply the spin orbit coupling. So here, even if we do not apply the spin orbit coupling, we are getting the band splitting. Generally, the band splitting occurs when you apply the magnetic field. Magnetic field in theory means you are applying the spin orbit coupling. Okay, but here in this type of materials, that is the characteristic of these materials. You don't need to apply the spin orbit coupling. Despite of not applying the spin orbit coupling, also you can get the band splitting. Okay,
Okay.
but
Okay.
for
Okay.
but it will break the like fundamental concept also, because to have the band splitting, you need to have a magnetic field. So there has to be some magnetic field, right? And DFT calculations, we cannot capture the direct dipole contribution here. So the one which is traceless is the octopolar moment. So because of this octopolar moment, presence of the octopolar moment, it is giving the kind of magnetic field. So because of that magnetic field, the band splitting occurs. Band splitting has to occur if there is a magnetic field. But here we are not having any magnetic field. But in theory, there is a magnetic field which is not captured by our DFT calculations. Okay.
Okay. Yes, sir. And oxygen, are they playing important role like they play in the case of high tissue superconductor, because there also oxygen plays important role in setting the magnetic ordering?
Maybe not, because not only RuO2, we have found out in FeSB2 also the similar kind of structure. So, but it has to
Okay,
be
sir.
non-magnetic,
Okay.
non-magnetic elements. Okay.
Okay. Okay. Okay. Thank you, sir.
So you see that there are so many ultramagnets, not only oxygen related. So there are many type of materials like MnF2 is also ultramagnets. There is no oxygen, right? And in our case, FeSB2 is also ultramagnets. There is no oxygen. So probably I think oxygen is not an important factor.
Okay. Okay. Thank you.
Okay, thank you.
Thank you, sir. Thank you for this wonderful lecture. Others may be knowing, but first time I came to know about this ultramagnets in our department also. First time we came to know about this ultramagnets. So thank you for this wonderful lecture, sir.
Thank you, sir. Thank you for your invitations. Hope we will meet again.
Yes, sir. Yes, sir. Yes, sir.
Okay.
I'll try to call you here.
Sure, sure, sure. That will be my pleasure. I
Yes,
love
sir.
to visit there.
Thank you, sir. Thank you.
Thank you. So shall I leave?
Yes, sir. Yes, sir.
Okay, thank you.
We'll break for 10 minutes, dear participants, then we'll come back. We'll have 10 minutes break, then we'll start hands-on training.
Yeah, okay.
FDF file formation, Siesta FDF file formation, and what are inside that. So, but I will take a little bit more time so that, because most of the people actually don't know, because I belongs to structural physics. So most of the people actually, I mean not all the people, the beginner. So what they are doing mistake is they choose a structure, but most of the people don't know about what should I choose and what I am choosing and for what purpose I'm choosing that. So let me share my screen first. So before going to the FDF file formation, I will start with the material selection. So the most important thing part is I will also share one of the PPTs where I also discussed about that what is important and what are not that much important. So always we have to take care about the material. So being explore zinc oxide too much. So I will start with the starting exploring material from material project. And you can use any database, crystallographic open database or any other one. So let's say I select zinc and oxygen from here, and then it give me a lot of information. It give me a lot of different structure. The crystal system are different. You see the triclinic, then hexagonal, trigonal, monoclinic, and orthorhombic and cubic, even cubic we see. So now the question is, which one should I select? So usually Professor Mohan also says, okay, look at the energy above hull. If it is near to zero, it means your structure is stable. Yes, I agree with him totally. If we should start with the stable structure, but along with that, we should keep other things in mind. Basically, you should then look at the literature, which zinc oxide phase, crystal system. Zinc oxide can exist in 3 different crystal system, hexagonal, and then we have woodside structure and rock salt, etc. So you can find that in literature. Then in the woodside one, which is the most stable one, and people love to work with them. And generally, when you are going to synthesize, the zinc oxide actually get this hexagonal structure with the space group of P63MC. And so I have to download. I need to let's say first you have to decide about the structure, which one structure I choose among them. So the correct, you should start with the correct. I also have here the zinc peroxide because I also work with this one, the zinc peroxide nanoparticle with the space group of Pa-3, that is a cubic structure. While I didn't never tried with this one, sorry, there is another one, zinc peroxide, but I tried with the cubic one. So because my synthesized zinc peroxide nanoparticle ultra small or quantum dots were that were cubic, and that their space group was Pa-3. So basically, the first step is selection of accurate material. So don't confuse about how many zinc oxide we have. If let's say let's say someone is experimental guy, and he synthesize zinc oxide, and he downloaded for the DFT calculation, he downloaded this one, cubic one. So actually your calculation will be totally wrong, and you will not get your experimental results. So first of all, we have to look at this. So I will click this card number. In the material project, it's called entry number. So after that, I have to look at the structure, whether the structure look good or not. People usually blindly download directly the zip file. Please, yes, I agree that in the any file that is uploaded to the material project or database that is cross-verified several times, everything is okay. But sometimes you by mistakenly, if you click the cubic one, at least you see I see that my structure is this one, and you can also verify from here. The result is with the P63MC with the band gap of 0.72 electron volt, with the predicted formation energy of these and non-magnetic, etc. So everything is written here. Then I can go a little bit down. So I always have to look this lattice parameter. Before downloading the zip file, I always have to look, that is, whether the lattice parameter are in the range or not. If they are not in the range, you believe me, you will I mean, if someone asked me why it would not be in the range, because sometime they calculated the zinc oxide structure under pressure at high temperature or something like that. So they use some external parameters, other parameter, we changed your latest parameter too much, so that are something else. So is it in the range or not? Yes, 3.24, 5.22 is in the range. Alpha, beta, gamma is fine. The volume is okay. Again, here they are again written with the symbol and point group, etc. So now we come down a little bit, and we then have in the material project, we have all these information about my material. One is about the phase stability, which we called usually in the DFT calculation, people start with thermodynamic stability. And here it is mentioned the method. You can see how people did calculation with different people have published about that and different etc. So about the phase stability, so we see the thermodynamic stability only, but you can also find, I think so mechanical is here. You can find mechanical stability, yes. So you can also find mechanical stability, and then electronic structure of, you will see the band gap, total density of state, and maybe projected density of state there. So everything is on this, then phonon calculation. Sometimes some of the calculation are missed, but in most cases they are available here. So then the X-ray diffraction pattern, it is not yet generated. You have to generate it. You have to look it. Okay. So what are the radiation source? That is copper K alpha with the wavelength of 1.542 angstrom, and with the shape factor of 0.94. You can change it, the shape factor, etc. And the peak profile is, the peak shape is Gaussian. You can change it to pseudo-wide function. Then they will show you the pseudo-wide function. Then even you can then change the crystallite size. It is written in nanometer. For example, if I decrease the crystallite size, so you will see a huge band, I mean the huge width of each. So you can also zoom in. So you see there is a big full width at half maxima. So this is a confirmation about, you can increase that well if. So So I don't know, something the Zoom restarted. Sorry for that. I'm. Can you people listen me?
Yes, yes, we can hear you.
Okay. Okay. So actually, what you can do, you can actually zoom in this space, and you can see they shows the uh, peak information, the HKL value for each peak, and two theta values, etc. So basically, you have to take care of all these things, and then I think so there is the other spectra too. I think so FTIR and time, the absorption spectra and optical spectra, you can also check that. Whole verification. When you verify and you are satisfied that yes, that my material is fine and I should proceed with that, then we go here and then we download the C file. So the C file is downloaded. So once the C file is downloaded, then what we can do, we can, yes, then what we can do, then we go to the Ubuntu system. Currently I'm working with because I'm online from my Windows system, so I will use WSL, Windows subsystem for Linux, to visualize everything. I hope so everything will be good. So let's see, the PWD is the print working directory or present working, what is the present working directory here. So then CD, I make one folder with FTP file name and then ls. So we have this C file.
Dr. Imran, Dr.
Yes.
Imran, just sorry to disturb you. Little bit slow. First, people should download that CIF file, and that will be confirmed by Dr. Gaurav. So the
Oh, okay,
people
okay.
should do
This
parallel to
okay, okay,
parallel to
okay.
us. Yeah, yeah,
Parallel. Okay,
yeah,
parallel.
parallel.
Okay,
Okay.
okay, okay, okay. Okay. Then please download this C file from the material project. If everyone is good with that, then we can proceed.
The file downloaded. Dear participants, you can let us know if you have downloaded Materials Explorer.
From material project, you can download this one because material project sometimes ask for login. Yeah. So you can log in with your Gmail account.
Materials project.
So they will report in the group or
Okay,
how
sir,
we
you
can.
proceed.
Hmm?
Proceed, sir, or if you have downloaded.
So is my screen visible?
Yes, sir, visible, sir.
Okay, okay, okay. So once you downloaded the zinc oxide C file, yeah. So you can see here the zinc oxide C file. Then, okay, so let me if someone are you
Just sorry for interruption. You can send the link as well, and they can also download using wget.
oh, okay. You mean link from here?
Yes, yes, sir. Yes, yes.
So I shared the link too, and so now we are going to, maybe some of the people don't know about how to share the, if someone are working with WSL, Windows subsystem for Linux, and they are not familiar with the how we can bring a file or a folder from Windows system to WSL. So the command for that is very simple. You have to type in this here in this line the backslash with the WSL name and with the then dollar symbol. If you write it here in the, it's called File Explorer. So if I enter, it will take me to the where Ubuntu is. Yeah. Then I have two Ubuntu. So I'm working this one. Then I always go to home directory. In a home directory, you will see your computer name or the name you given to your computer. So when you click that, you will see all the folder and file you have in the system. If you never worked with this system before, so there will be no folder or something. If you have here the I downloaded zinc oxide here. You see it is in the Windows system. I can copy. I will copy it and then go to here and then we'll paste it. It will ask for replacement. Let's say because I already downloaded before, and from the Ubuntu system in the, let me show you how to work with the WSL. So for the WSL, you have to go to control panel first, and in the control panel, it will open a new window, control panel. Then you go to programs. Yeah, in the program you see there, here we see the turn Windows features on or off. You must click this one. It will again open a new window where in the last you see there is an option, we call it Windows subsystem for Linux. Last, you must check this one first. Those who are new, they can go through this, they can check this one. When you click OK, it will ask, it will take a little bit time. You have to wait because they have to activate the Windows subsystem for Linux for you, and it will then ask for you to restart your system. Without restarting, you can't use the WSL. So you have to restart it. Once restarted, still Ubuntu is not there because we only activate the Windows subsystem for Linux. We didn't install the Ubuntu. So you will write here Microsoft Store. So in the Microsoft Store, if you open it, it will open like this. They will not ask anything about something, but you have to just type Ubuntu 22. So 22.04. Keep that in mind. You should always write LTS. LTS is the stable version of the Ubuntu. Okay. So when I enter it, so in my system, it's installed already. You see, Ubuntu 22.04.5 LTS. So when I click it open, so it will open. While in because I don't have this one, so it's it will in those in the system of those don't have the Ubuntu, they will see here a get option. So you must click this get option, and then it will install automatically. After installation, you will see this icon 22.04, or you can, if you didn't see, because I use it frequently, so if you can't see any icon, you should type here Ubuntu, so it will come out like this. You can then pin this to the taskbar, so it will come here, appear here, yeah, or to the start, which you in which style you need like. So then after that, you can work with this WSL. So if anyone is working with this WSL, then we can, and he or she want to install it, we can wait them. We should wait for them, or I can proceed.
Let them
Gaurav.
respond.
Yeah.
Let them
Okay.
respond, sir.
Okay. Okay.
Dear participants, if you have done, can we proceed? So I think we should proceed because we have less time also.
Okay. So now after installing and preparing the system, then I come here to this. So what I will see when open it for the first time, let's say exit from this. So let me start it again. So I will see like my name, and with the computer name, this is called username @ computer name, then colon, and then with the dollar symbol. So after that, I first type pwd, present working directory is this one, and then I created a new folder with the name of fdp. Then I can ls again. So I have a zinc oxide C file. So with the GDIS, I can open it. So if the GDIS is not installed before, you can install with the sudo apt install GDIS with this command. So if someone want to install, they can use sudo apt. If someone says, okay, you forgot the get here. So nowadays apt is working well, and sometime we need get, but if you want to type, you can type. It's not an issue. So this is a command to install the GDIS. When it installs, so I will write here only the GDIS. It will open a new window like this. So in this window, the first thing is to open the C file. So when I open the C file, I will look at my C file, the geometry and everything of the system. And after that, I will save this C file as again as a C file, because the C file downloaded from a material project sometime make issue with the FDF file we created. So it would be better that the C file you download from material project, open it with the GDIS and save it as C file again using GDIS, because GDIS write it in their own format. So now I can close this, because this one is still a C file from the material project. So I will close it from this small cross button. So I close it. I will open it again and double click it. Then it will open. Now I can save this C file using the same save, and I will click on this name and I will write here FDF. So it will create the FDF file for me. So before closing the GDIS, I will minimize it. I will go to the folder and I will see whether it's they created the C file or not. Sorry, FDF file or not. Yes, the FDF file is there. I can see clearly. If I right click on that and open with Notepad++, if someone don't have Notepad++, they can also use Notepad. So it will open like this. So the first line in this, can someone try with the zinc oxide unit cell to create the using GDIS now to create the FD file? So I don't know, people are not responding anyhow. I can continue. Yeah. So the first line, the hash symbol in the FDF file is known as comment. So the program or Siesta will not read this first line, while each first line is about the GDIS version and which version, by which version it is created. This is intentionally left comment. We can delete it, or we can. The second thing is about, before going to the detail of this FDF file, I want to share one PPTs. So the PPT is about this. Is it visible?
Yes, sir.
Okay. So let's proceed with these PPTs. The PPT is full of information about the FDF file, and let's enjoy it. So first of all, we have to look, because we are attending this session since last few days, so everyone is familiar with Siesta, so I should not spend too much time on that. SPEN is initiative for electronic simulation with thousands of atoms. And the second thing is that it is DFT based code for material simulation. And the third thing is efficient for large systems, especially for surfaces and nanostructure, because Win2K is, I think so, using the unit cell calculation, and it's Siesta have a lot of flexibilities to perform a lot of calculation. And the most important thing is they use localized basis and real space grids. So they don't use the plane wave approach. So these are just the first thing is about the creation of structure, and after structure, when you are satisfied from your structure, then you can proceed with the calculation, DFT calculation. And after DFT calculation, then you can also perform you can also cross verify your result through experiments even. So overview of a siesta input file. So again, there are many parts in the siesta input file. The first part is about the system information. The system information must be systematic and meaningful. But believe me, it is not that much important. And what the system information means here, and where we can find it in the siesta input file, in the next slide I will explain it. Yeah. The second thing is geometry setup. I mean the selection of your material, the accurate material and the accurate geometry, and etc. We already discussed it about that a little bit. So this is the most critical step, because this is the turning point. If you started with the wrong parameter, with the wrong structure, you will never succeed it. The third thing is the K point and grid. So basically, this is the second most critical steps. So in an easy language, basically crystal exist in real space with the atoms and their position in a crystal, especially in a box, let's say, while after the Fourier transformation of this real space into momentum space, we call it K space also sometime. We call it momentum space. So these K points actually comes from the brilliant zone. We called a unit cell in a real space, while the same unit cell in a reciprocal space, we call it brilliant zone, which are defined by K vectors, momentum vectors. So this is the most critical steps because your calculation totally depends on that. And the grid, actually, the example of the grid is like, what is the value, what must be the value of mesh cutoff? Yeah, if you choose a lower mesh cutoff, you will lose the resolution of your your calculation, your accuracy of your calculation. So the grid is like okay, I can give an example like a picture, where in a picture, if you have low resolution picture, you have less pixels, while in a high resolution picture you have more pixel. If the mesh cutoff value increases, basically you are increasing the resolution, the resolution of your accuracy of your calculation. So we must do convergence test for K points and also grid. And fourth thing is the calculation parameters. In the FDF file, we have then calculation parameters, and a calculation parameter contains several parameters, and for that you have to look the Siesta manual. I will also explain some of them, but that depends on several things. And the last part of the FDF file consists of output options, and for the output option depends on the purpose of the study. So maybe some of you ask a question, what does it mean? It means, what are you asking from Siesta? What do you need? Let's say I need absorption energy, or I need the I want to look for the interaction of molecule with the surface of my material. So for that, border analysis or molecule population is important. Yeah. So depends on and what type of calculation you are, whether it is a single point energy calculation or relaxation or MD run. So depends on. That is totally the output option are depends on this, but Professor Mohan and their colleagues developed some journalized, very precise FDF files from their experience. So that contains all these parameters you need during your study. So system setup example is like the first part where I told you about the what is about system setup. So the system setup consists of few lines in the FDF file where system name is defined. I in the previous slide I showed that it must be systematic, the system name. The system name not should be long, too much long, but it should be systematic that you can, if you forgot something, what because some people are doing calculation for several material, just like it is zinc oxide, hexagonal structure with for the unit cell or for the surface with the space. So you can I mean write it here with a shortcut, just like I wrote here zinc oxide underscore unit cell. So I will remember that this calculation is performed for unit cell. Then the system label, which is very critical. I mean, you should not you should not name many material with the same label, because same label are used in further calculation. So in case of layer structure, you must write the system name like zinc oxide underscore 221 layer underscore, I mean, one layer and underscore 10 angstrom. This is actually vacuum along z axis. So for the system label, shorter than the system name, no space or special character. Don't use such things. Unique per calculation, avoid duplicate in the same folder, because it then it will replace your previous calculation. So next is in the FDF file, it will look like this. We will go through this each section in the FDF file, and then defining species. In the we call it block. In the block, the blocks start with the percent symbol, log, chemical species label. Then one is zinc and other is oxygen with the atomic number of 30 and 8. Then in block, chemical species label, which is block. Keep that in mind that this zinc, this zinc name must be similar to the PSA file name of zinc. If in the PSA file, if you downloaded a PSA file for zinc and it is named like zinc underscore something, then you must write it here, the zinc underscore something. Otherwise, it will create an error for you. So how it will be look like now? The system name first, and then system label, and then next is the okay. This is the actually the if pseudo potential is in the same folder where you are performing the calculation, then we don't need this line. Otherwise, you have to define where my pseudo potential are. For that, this dot is very important. Then forward slash, then the path or path to the pseudo potential file. So next is the how many number of atoms are there. So we have for the zinc oxide, we have 4 atoms with the 2 species. Then this So this block is the chemical species. I also wrote here must be same as zinc PSF. If look at your PSF file name, if it is written here zinc, so it must be zinc. If it is written here oxygen, so this should be O. If it is written oxygen.psf, so it must be like oxygen. So it depends on the so the next is the lattice parameter. Then we define, we call it geometry setup. So we define the lattice parameter. So the first, I will repeat the same thing several times. So the first is zinc oxide surface, then label with the system label of zinc oxide with 4 atom and 2 species. And sometime we need this line, but mostly no. And number of atom 4, number of species 2. Then the chemical species label block, and then we define the last one, the lattice parameter, where the first line is the lattice constant 1.0 angstrom. So 1.0 is called scale factor, and this scale factor is basically, this scale factor is basically then multiplied with each lattice parameter. So this scale factor is then multiplied with each lattice parameter. And for example, if we get like here after optimizing the structure, we get like 0.9. So siesta multiplied it automatically with this, or you can do it manually too. So the next one is the atomic coordinates. So still we are in the geometry section of our FDF file. So I will, because the whole FDF file didn't fit to the slide, so I use here the atomic coordinates format. First line should explain which format we are using, either fractional or Cartesian. We can use both of them. So at the moment I choose fractional because GDIS create the fractional coordinates for you. So the next is a K-point grid. So first of all, we must know about the K-point grid. So what are K-points? Are like sampling point in electrons playground. If there is a playground of electron, and we are sampling some points, and we are checking whether how much electron density is there, and we, on the basis of that, we are calculating, we are taking that part and we are calculating the electron densities. So basically in a reciprocal space we call it brilliance zone. While electron have different energy at different K points, more K points, better accuracy but slower your calculation. It is if you increase the number of K points, yeah, so basically the accuracy become very high, while the computational power increases too much. And next is low resolution. Example is the low resolution photo and high resolution photo. Few K points means fast but blurry result. Many K points means slow but sharp result. Now maybe someone asked me, what does it means? You are talking about K points. So I will give an example, like I'm taking some one. Let's say we can consider the floor of our room where we have tiles. So each tile, if you want to do some testing for these tiles, so for the whole room we are not able, maybe we have a big big room. So for the whole room, it is not possible to do the testing. So we select in each tile a small portion, and we test there what is the material. So basically, K points is a similar that we have a crystal with repeating unit cells, while crystal is infinite in nature. So basically, for the infinite crystal, we can't perform the whole calculation. So for that, we consider the K points instead of the whole crystal. So what a K points grid, I'll already discuss about that it basically defined by mesh cutoff how much resolution of how much precise your result must be. The next is how to choose K points. This is important question. So for bulk material 3D, use a grid like 4 cross 4 cross 4 because we have periodicity in all 3 directions. Yeah. While for the surface 2D material, use a grid like 4 cross 4 cross 1 because in the Z direction, which is non-periodic, so we will not consider any because we are not sampling there anymore. So we will take one in that direction. For the molecule, we take always 1 cross 1 cross 1 because there is no periodicity for the molecule. So rule of thumb. So what must be the rule? Smaller cell must need a denser grid, while larger cell need a fewer K points. Why? What is the reason behind it? Because we are transferring our crystal from real space to reciprocal space. So if a material in a real space is small, like a unit cell are small, so in a reciprocal space it becomes bigger. Yeah. So for the bigger material or the bigger, because we need more K points to calculate accurately the electron density, potential, etc. While for the large cell, if we have in the real space we have bigger cells, then in the reciprocal space it becomes smaller because they are Fourier transform of each other, so it becomes smaller. That need that need fewer K points. So after that, how it look like the block is look like 4 space 0 space 0. So this is along x-axis, this is along y-axis, this is along z-axis, but it must be for bulk material. Yeah, and there must be one line of end of block. So this one is 881. This is for the for the 2D material because we have no periodicity along z direction, and this one is 111 because we for the molecule we should add space along x, y, and z direction to the molecule. So we will take the K points grid like 111. So what is the Monk-Spec K points scheme? So basically, you can also see in the literature, but it gives you even sampling, better sampling in case of instead of other schemes. So then another block is for the constraint and relaxation. Yeah, for the constraint and relaxation, let's say I have this geometry and I optimize it, so it become like this. Yeah. So before optimization, I place the one molecule on the top, while after optimization, after placing this one, so what I do? What will I do? So I will take first of all a unit cell of zinc oxide, and I will optimize it. Then the optimized unit cell will be extended along X, Y, and along XY direction so that it make a plane. Then I place this optimized molecule on their top, but for the during the calculation, I will keep this layer fixed. The reason behind it is if you allow them, it will distort the whole structure sometime. So we have to fix this layer, and we will allow this molecule to go up or down because of the charge density difference between these their charge densities either repel each other or attract each other, depends on nature of these atoms. So basically, this whole system depends. So this block actually constrain the position of atoms for this layer from 1 to, let's say, 18. So from 1 to 18 in the atom. So you have to count it from 1 to 18, and what is the number of which number assigned to citrate molecule. So this organic molecule. So we have to take care of this. So we can fix this layer, and we will allow this molecule to either move up or down during the calculation. So another one, we have DFT parameters, the basis sets, the basis size first. So we use the DZP, double zeta polarized, or basically triple zeta polarized. So what this explain for you, basically this the atomic orbital which are spread over the region, and double zeta polarized, basically double zeta. It is like an example of whether you are using you want to draw something and you use a single pencil to draw it, while double zeta means you are using two pencils to draw this one picture with the shadow. So basically, when you increase the basis size, the more accurate result you will obtain. And the next one is the PAO energy shift. This is also depend. I mean, this is the related to the electron orbital, and type of run we have, that is a conjugate gradient run, where we calculate the total energy of the system and then move our system a little bit, and then again calculate the total energy, and then compare with the previous one whether what is going on with it is decreasing or increasing. So this is basically, we call it the convergence criteria, where we told to the siesta program that the maximum force must on each atom, if reached to 0.005 electron volt per angstrom, then you must stop the calculation. Then it's enough for me to do the further calculation. The mesh cutoff, we already explained about, I already talked about that it must be in the range of 100 to 400 or 500. SCF and the exchange correlation functional. So how many iteration we choose for the self consistent field calculation, where self consistent field calculation means the distribution of electron must be consistent around the atoms. So for that we do iteration so that we can accurately calculate the charge densities and potential from there. So the next is the DM maxing weight. If you calculate the charge density, how much weight of the previous one should I consider? That should be about 0.02. Then number pole, you can check that in the siesta manual. Then exchange correlation functional, either we can choose GGA or LDA, depends on the nature of the material you use. Then along with that, you must write the exchange correlation functional author who wrote that the PBE are for GGA and LDA. For the LDA, we have CA. And then what type of calculation you are doing? We are doing the calculation at room temperature. So what are the output options for us? Write the coordinates for us, which can be readable by xmol. It will create a file with the extension of xv, and write Mulligan population, that what it tells us about. This will write atomic charges, orbital population, and spin population to the output file. Row, save row line, that if the save row line is true, so what will it do? Sorry. This will create a 3D electron density data for the post processing, like charge density plotting, etc. And in the last one, if you write save use data true, what it will do? It will run the calculation. If you have previously DM file or row file, so it will avoid to run the calculation from scratch. So the two more slides, then we can go to the FDA file. So the DM use save DM true. If this is true, this line, then it means read the DM file from the previous calculation and use it as initial guess for the SCF loop iteration. And MD use save XV true. Continue with the MD simulation from molecular dynamics simulation from where it left off by using the last known atomic position and velocity. The next one, if this line is true, MD use save CG. Basically load the CG related information like force, step history from the save file. And best practice is to initially start with a small system, then always visualize the structure. I already discussed it about that very deeply. Tune mesh cutoff and basis set, and also basis size. So check the convergence carefully. The convergence must mean some, without meaning convergence doesn't matter. So now I will go to the FDA file. So from the FDA file, we will copy this system label. So the method is very easy, that we downloaded zip file from database, and we convert this zip file to FDA file using GDIS, and this GDIS will create the atomic coordinates for us and everything here, you see. So I will copy from the system label till the coordinates. Keep that in mind, from system label till coordinates. I will copy it, and we have a script developed by Professor Mohan and their team. So you can paste it from system label to coordinates. Now we will go through this one script, then I can answer any of your question if someone have issue with the script. So in the script, we ask the program to make a directory, yeah, and then you have to go to the directory, And then again in that directory, make another directory. mkdir means another directory. Then I use for loop for I in range, just like in Python we use for I in range this. So here in Linux bash script, we use for in sequence with the initial value and final value with the step size. Step size means first it will take 50, then it will increase by 50 more, then it will become 100, then it will increase by 50 more till it reach to 500. Then it use do loop, it will repeat it many times. Dot, this dot is very compulsory. And then the name of the the name of the FDF file it will create during this calculation. So basically the FDF file start from here. So it is the same thing. I wrote it here like system name zinc oxide. I can also write it here the zinc oxide for unit cell, and the system label is zinc oxide with the number of atom 4, with the number of species 2. How it look like the PSF file. So I must save the PSF file, like if I download the PSF file from here. So I will write here the pseudo potential. You can also download it from Cornell University. If you go there, Cornell University, and you go to the periodic table, and I download it. I will click on zinc, and the zinc. If I right click on it, it will give save link as. So look at the name of this specific file. It is written zinc/gga. Yeah. So I move this two things, because in the FDF file, if I open the FDF file, in the FDF file, in the chemical species, it is written zinc, not zinc-gga. It is written oxygen O. So it must be consistent with your PSA file, these two lines. Yeah. And then the latest constant with the latest parameters A, B, C, alpha, beta, gamma. Then atomic, then you choose the K points grid with the log start from and each here with the one. Let's choose the higher. But we don't need. This is the geometry constraint block where I Sorry for the interruption. The zone started by itself. So this is the geometry constraint block where you constrain some of the atoms while allow some of the atoms. Yeah. This is basically we call the DFT part, where you tell to DFT consider double zeta polarized with an energy shift of 0.03 electron volt, with the type of run, the conjugate gradient. Use this one method and run the molecular dynamics run, where the iteration value of 300, maybe 500 is best in some cases. In some cases, 300 is okay. The SCF must converge when you draw it. You can draw it, make it true or false, depends on your calculation. The number of step consider 0 is drawing a single point, comma point, and if it is your atom relative positions, maximum force on the atom. So this is called convergence criteria, where you define the total energy, they calculate the force on the each atom. When reached to 0.005, then we must stop. The program automatically stop their calculation. Mesh cutter is the grid for the points. Yeah. So basically, we put a dollar symbol here. The reason for this is that we will find this value, a best mesh cutoff value. Yeah. And then the mixing weight scheme, which basically define the how much charge density I should consider with the I mean how much weight of the previously calculated and the new calculated charge density, how much I should mix them. Yeah. So if you increase this value, basically it will take the old one. If you decrease this value a little bit, it will totally depend on the new one. So decrease this value totally depends on the new one. That will definitely increase the computational power. So DM number poly, and then coordinate XMOL. I already explained this all in the PPTs. So this one is a new one. Basically, they use, okay, in the reciprocal space, if someone have already did calculation, so basically matrices use a faster calculation compared to other methods. So basically, we use diagonalization method to solve the matrices for during this calculation. And then finally, we say, okay, save row for that. For the we can also uncomment these commands lines when we need it. Yeah. So basically this description for the mesh cutoff calculation. So for the mesh cutoff calculation, we don't need to save everything for us, because this will make because the folder will be deleted after. And I don't think so that we need this one. Yes, during the optimization calculation, we need all these 4-line uncommented. So this is the basically. And the other thing is that for the other properties, like for the total density of state, for optical properties, for other things, you always have to add here a new block. And from where you will get this block? From the Siesta manual, or we can provide that to you people. So anyone have any question or created such FDF file or some issue while during the creation of this FDF file, they can ask me.
Dr. Imran, sir.
Yes.
Sir, I want to ask one question regarding the K point selection, sir. And
Yes.
if I have a hexagonal structure, sir, just like cobalt hexagonal, so it is a bulk structure. So shall I have to take kx ky same, or it will I have to take it as different? Means kx ky is same and kz different, somewhat like that.
Basically, this scheme basically suggests that you should then select same K points. Yeah.
Yes.
For example, for the bulk, if you take it like this one 8, then it you can take it to 8 also and 8 also. You should not take uneven numbers. You always take even, the even distribution of K points. Yeah. If you remove this scheme and you insert, I have to go through the Siesta manual, whether Siesta manual have other scheme too, then you can use 8, 2, 1, such like K points.
Okay, sir. Thank you.
But believe me, the K point selection and mesh cutoff selection and the um the correct geometry basically is the key points of success of your calculation. So anyone have any question, they can ask me, please.
Dr. Imran, I think you should share one template to create one FDF file by following the method we have explored.
So I should send them the zinc oxide C file, yeah?
Yeah, just zip, like, they have to download that zip file of their material of interest and just share that one template and try to make one FDF file. So tomorrow we can continue with their FDF file or whatever that material which will be easy to run. Uh, because zinc oxide, this will take time, na? It's a bigger
No,
element.
it will
How
not
many
take
items are
time
there?
because
How many items are there?
4 atoms. 4
4 items.
atoms.
Okay, okay, no issue. All right. So this is
Yeah.
that zinc oxide. This is hexagonal. Hexagon, this zinc
Yes.
oxide. This is yeah. Okay, nice. No issue.
For the moment, we take the K points 444 so that it run easily. This is okay. We will take this 300 and so you can open this FDF file with the Notepad++ or Notepad, depends on. So I share the file and the zip file, both of them. So anyone have any question about that? You must go through this and then. So Professor Mohan, I think so. It's over from my side, and you can at the Garu can
So
talk.
I think you should complete the first sister run because the people have, we believe that the people have already installed the sister in yesterday's session.
Mm-hmm.
So first sister run we can perform today. So Fazal will continue.
So for the but I'm now on the Windows system, and
Okay.
I don't know.
Okay. No issue.
I don't know exactly about whether I have here. Just a minute. Whether I have the siesta here or not.
When your WSL sister is installed on.
Yes. So basically, the issue for the, and you know that WSL always misbehave about that, but yeah, siesta is here. We can start the. So let's today we can start the first run of mesh cutoff value calculation, that how to calculate the mesh cutoff value for the
No.
K
Do
point
not
grid.
use the script. Please. Imran, please. Do not use the
Yes.
script. Just a single FDF file. Create that FDF file and run for 0 step.
Okay.
Then that this will cover in the optimization process.
Okay.
Yeah.
Okay. So here we have to go download the PSA file. for zinc and oxygen. So basically for the siesta run, we need these three files. One is the input file we created during this session. The second thing is the PSA files. Because we have two species, so zinc PSA file and oxygen PSA file. So then after that we can clear the screen for us and then ls. So all the necessary files are there. If you want, you can delete other files, but I mean that will not take part in the calculation. The only take part in this calculation is this zinc oxide FDA file, then zinc PSA file, then oxygen PSA file. These three are the important files which will take part. So let me try, maybe it will not make an issue for us. Let's, okay. So MPI run, this is for the parallel run. I'm going through this for the parallel run. And minus, we call it flag, NP. We use NP for number of processor. So at the moment I will choose 2. And then I will use the executable siesta because I check it before. If you don't remember what is my executable, then you can type here siesta and double tab. It will, if it shows siesta here, that it means your executable is there and you can use it. So again I write the command mpi run minus np, and then 2 of the processor will be used, and then I will write the name of executable siesta, then the input file name. If you don't remember, just double tap button, tab button, then you will show what is the FDA file. I think so I have 2 FDA file here. Let me verify which one is for the calculation. One is the small one and other is the big one. So I think so this one where we put 300 blah 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 etc. 44. Yes, the smaller one is because we look at this. I see in the, when I double tap, I see 2 FDA file. One is this one and other is this one. Yeah, we will use this one because we prepare this one. Then zinc oxide dot FDF, then pipeline, and then the command is T result dot out. So if I enter, so what this command total command means, the mpi run is basically a program that that actually run the siesta in parallel for the parallel calculation. Then we flag one word np, and this negative symbol say is always used for flag, and this np is number of processor, and I told to the system use only 2 processor of the available, and then the executable, the third place must be for the executable, fourth place executable, I mean this thus, and then after which input should siesta read, I then specify read this input file, and then the pipeline actually then give you the interactive calculation. The calculation you can see, you will see here. So t result.out file. So I pipe this calculation to shows the result.out file during this calculation on screen. So if I enter, so basically so basically they give some error. Maybe MPI run is not detected for moon or one process. Yes. So maybe my I am on Windows system, and maybe my MPI is not properly installed. So we can start this calculation sometime. Maybe, or I can also use with the single core siesta less than input. Sorry. FDF T result data. Then it's run, you see. So basically, if because my MPI run was not working properly, so that's why it failed to